Greetings and welcome to the Artifact Electronics channel. In this episode we'll be looking at a Tektronix TDS 460 4-channel scope. I picked this up through eBay and it was sold as non-working, actually not working correctly. So I got it for a very reasonable price. It's in good shape physically. I have already cleaned up the outside a little bit, but as I mentioned, there seems to be a problem with it. Now quickly to run through the specs, as said before, it has 4 channels at up to 350 megahertz. It's a digitizing scope that will take up to 100 megasamples per second. Has a bit of a Spartan control layout in what they've done here, even though it does have 4 inputs that do automatic probe detection. There's only a single set of controls for vertical and horizontal positioning. So the way this works is each channel can of course be turned on and off individually, but whenever you want to modify the vertical or horizontal for a channel, you need to select the corresponding channel first, and then the controls will affect the channel that you have selected there. There is the trigger control section, the high-level menu selection, and the soft keys along the side and bottom of the screen that let you take menu actions. It's probably interesting to note that this scope was one of the last scopes that Tektronix made that offered a CRT screen before they switched over to LCDs. But let's have a look and see what the scope is complaining about. So let's get a better view of the screen and give it power. So the control panel lights up, screen lights up, get your little clock face here, I guess the please wait message. Please wait some more. And the lights are still all on. It's doing something, but the lights are still all on. I hear some relays clicking. Oh, the lights went off. And it's putting up a grid, turning on channel 1. But then it is telling us that it failed the acquisition test. So what that means is that's probably what will affect display of signals. But let's have a look and see if in fact that is true. So let's clear the menu and put a signal into channel 1. The simplest is probably the probe compensation signal over here, of which we see nothing. Channel 1, indicated by this light, is active, is turned on, set to AC. The screen works pretty good. It's a little bit weak when seen in real life, but it's pretty sharp and very readable. But channel 1 is on, we are injecting a signal into it, nothing is showing up. The best cheat is to press the auto set signal, which essentially attempts to analyze the incoming signal and sets everything up correctly. But it is not, there is no signal. And as you may see over here in the trigger section, the ready light is on, but it's not triggering. Now we can force it to trigger and it will briefly triggered, but still nothing shows up. So basically the failure of the acquisition board means that it's not acquiring signals. So what we need to do is open up this guy and see what things look like on the inside. I've done some research on these sort of scopes, and one of the most common problems that they suffer from is that the electrolytic capacitors start leaking. And it's not just some of them. They do it in a group thing. They all start leaking at the same time. And the electrolyte that leaks loves to eat copper, so it starts eating traces. The problem with that is the capacitors, observing the capacitors and replacing them is a deterministic problem. But finding out what traces may have been damaged is a totally different story. Now this scope, as you can see, it powers up, it seems to work, it looks okay, so let's see if we can find what the problem is by poking around the acquisition section and mostly doing a visual inspection and seeing if we can see anything that is that looks out of order. So let's continue and take the instrument apart. I've removed the cover, and here's the top of the scope. Quick run through what we have in here is the AC input and conditioning board, the switching's power supply over here, the CRT driver and the CRT underneath it. You can barely see the front panel PCB that holds the switches, pots, well, they're not pots, they are rotary encoders, of course, and a small card cage on the side that has 3 boards in it. This board is the GPIB board, the board on top with a GPIB connector on the back. The next board is a video board that has a CGA connector on the back. And I guess I don't have a CGA monitor handy, but I guess you'd hook up a CGA monitor and it will give you the CRT image in full size, glorious color, whatever. There is a third board that doesn't have a connector on the back, but it's labeled as the 1 meg option on the rear panel, which is shown as an option down here. And that board basically is populated with RAM chips. Now, the board that we are really interested in is the main board, which sits underneath, and that's where we're going to start looking. So I flipped it over. We're looking at the underside of this scope right now, and this is the main board. We have, of course, the main processes, which are 2 DSPs over here, surrounded by RAM, I suppose. We have the acquisition ASICs, 4 over here, another 4 over here with large heat sinks on them, and another 4 over here, also with heat sinks on them, and another 3 here. I haven't dwelled that deeply into the schematics and theory of operation, but whatever problem we have is here somewhere. The inputs come through here, are processed in this through here, passed on through this connector board to the main board that probably acquires the signal through these chips, processes it, and then displays whatever it sees on the display. Let's have a little closer look at the capacitors and see if they'll give us a hint as to what may be wrong here. So actually, jumping forward a couple of hours, once I started observing things, it turns out that most of the capacitors were leaking, and there was corrosion apparent on many spots on the board. So I started the task of removing the capacitors and replacing them. Now, the way to remove these, it gets kind of difficult when they have corrosion on their solder pads. These are already replaced, so the solder pads are relatively shiny on these. I mean, the way I do it is I use a heat gun with a relatively narrow nozzle. I first heat up the general area by playing the heat gun at a distance over the affected area. And once the board is warmed up, I will make a mask out of aluminum foil. This is just a demo, it's not cut to scale, but essentially with a cutout in it that only gives access to the capacitors or to the components that I want to remove. I then direct the hot air over that component, and it comes off rather easily. It prevents damage to any neighboring parts, but more importantly, what it prevents is, in this case, you can see there are a lot of surface mount passives over here. And it's very easy that if you're not careful with the heat gun will not only melt the solder, but the wind will also possibly push these components off of their pads. And once that starts happening, the entire endeavor becomes much more difficult than it was at the beginning. So I've had good results with using the aluminum foil mask and masking off everything surrounding the affected components that I want to remove. Now the interesting thing was, yes, most of these had leaked, and when I heated them up, one of the reasons they came off so easy was I would heat them and the bottom of them would blow out, automatically blowing the whole component off the board with stuff oozing out of it, which was the electrolyte. About 50% of them actually blew off their bottom, not their top. The others came out in one piece, but I did a sample measuring of all the ones that I've removed, and every single one of them was open. So I didn't find a short, even though I don't know the ones that blew off the bottom. Some of them may have been shorted, but I don't know whether open capacitors would cause a complete failure of the acquisition logic, but I have now replaced all of the capacitors on the main board here, and we should probably power it up now and see what good, if any, that did. Before moving on, I wanted to show a different section of the board. These were 4 caps that were replaced also, but you can see the corrosion on the heatsink tabs of the regulators over here. I mean, I've removed the worst of it, but what you see just won't come off. So there's corrosion all over this board, and I did a visual inspection. I couldn't find anything damaged, but this may be an indicator of other problems that may still exist. But anyway, before being overly pessimistic about this, let's power it up and see what the self-test will tell us. And now for the moment of truth, let's turn it back on. Looks about the same as it did the last time, except I don't know what to expect when it's working correctly. I hear some chattering relays, the please wait message, and now it's telling us we got a failure on the acquisition attenuation board. I thought that the last one was on the acquisition board, but I can't be sure. I'd have to watch the video. But obviously we have not fixed the problem. My guess is there are some traces that have been damaged. So I'm going to sit down with a magnifier and spend some time looking at the main board again. And when we come back, hopefully, we'll have some results. So another few hours have passed. I think they're starting to deliver newspapers outside by now. But I did find something. And what I found was this. There's a pair of voltage regulators over here. Those are, what are they? LM2990s. And they're negative 5 volt regulators. And there's a pair of them that I guess generate two independent rails, minus 5 volt rails over here. Now the first thing I found was the one on the right over here. Even though it was, well, the one on the right wasn't getting any input voltage. I mean, it wasn't putting out anything, it wasn't getting any input voltage. So what I did was I jumpered the input voltage from the one on the left to the input pin of this guy. So he was getting input voltage, had a good ground in the middle, but he wasn't outputting anything. So so this regulator was bad. So great, you know, I pulled the regulator. I had another one that's the same type, except the one I had doesn't have the full heatsink tap, but I guess that's just going to have to do until I get the part with the big heatsink on it. And at that point what I did was I also jumpered the input over here to the capacitor. So basically at this point there was a break in the trace leading from the capacitor to this. The capacitor was getting the input, the unregulated input voltage, but it wasn't making it to the regulator. So after I did that, I turned things on and it still failed. So I started checking some more. Now I noticed that this was generating minus 5 volts, but they weren't getting to the capacitor either. So the trace leading from the output to the rest of the circuit, to the rail itself, was interrupted. I checked it and I couldn't. I wish I could show you, but I really can't because it's hidden under the solder mask, and I wasn't going to go in there and scratch off the solder mask because I pretty much knew what was wrong. So I jumpered that one over here. And then finally, after my bad experiences, checked the other power connections and noticed that the output from the first one was also not making it to the capacitor, to this trace over here. So I jumpered this one too, and then measured, then powered it up and measured a few things, and now all of a sudden the minus 5 volt, the pair of 5 volt rails was live. It's interesting because on the other side of the board there's a similar circuit with plus 5 volt regulators, and that one worked, had no broken traces or anything like that. So let's hope that this one will do it. And so let's switch things around and power up this guy yet again and see what it has to say this time. All right, ready to test again. So here it goes. I mean, I'm not exactly sure what's supposed to happen when everything works right, but so far things look like they did before. Please wait. And wait some more. Oh, it did a galloping sound with the relays this time. I don't think it did that last time. And it did 4 times. And it's telling us power on self-check passed. Could it be? Well, let's first inject a simple signal into each channel and see if it shows up on the screen. We're just going to use the calibration output on the scope. So, first what we're going to do is turn on channel 1. And instead of twiddling knobs, I'm going to use the convenient auto set feature. But first let's make sure that we're triggering off the correct channel, and we are not. It says trigger on channel 4, so let's go to 1, and there's our signal. Time base can change, amplitude changes. I guess what it's doing is it's showing us here where the trigger point is. And this, of course, I don't know if you can see it, but it's a 1 with a little arrow on it that's showing us the 0 reference for this channel. And let's see if we turn the trigger knob. Oh, it is showing us in the bottom right corner what it's triggering off, and with something in AC, it's probably safest to just set it to 0 volts. And you can see it is triggering on the rising edge. Now, if we go back in the trigger and change the slope to descending, we can see that it is now triggering on the descending part of the incoming signal. So that part seems to work good. Let's go back to ascending. Let us turn off channel 1. Move the probe to channel 2. Change the triggering source to channel 2. And turn on channel 2, and there you go. Channel 2 is displaying the same waveform, reacts to the time base and the scale, and we can see it's triggering on the rising edge. So let's see if it also triggers on the falling edge. And it does. Notice that this little marker here has changed to a 2, indicating the ground reference of the number 2 input. So far so good. Let's turn off channel 2. Go to channel 3, set the slope back to what it was before, change the source to channel 3, and see nothing, but we haven't turned on channel 3, and there's channel 3. Now notice channel 3's reference is way down here. So let's adjust the vertical position. And this little marker changed to a 3, indicating that this is channel 3. We can scale this to square wave, the timing, and the amplitude. And that is good. Channel 3 is functional. So channel 3 will get turned off. and we will go into channel 4. Same song and dance, go to the trigger menu, change the source to channel 4. Slope is still on the rising edge. And we turn on channel 4. And there you go. Channel 4 is also functional. So it looks good. We didn't try the falling edge triggering on channel 3, but let's try it here at least. And sorry about that, we can see that now it's triggering on the falling edge over here. And back to the rising edge. And that looks good. Another thing we should probably do is see if it displays 4 simultaneous channels. I'm not going to dig out three more probes here. I'm just going to put up a ground line for those scopes, for those channels, and see what happens there. So just do a force trigger, bring 4 all the way down here, then we turn on channel 3 and bring channel 3 down and force the trigger, and we got 2 traces. Channel 2, a little bit up, and channel 1. So they're all there. And so basically now let's put it all back together and put in some external waveforms from a function generator and see how those look. But it sure looks like this guy's been fixed. So on to the final test. We're back, the scope's put back together, it booted up. At first it was a little bit confusing because when I booted it up it kind of showed me where we had left off last time with showing the different offsets of all 4 channels on and basically showing ground references. But then I figured out that, yeah, wait a minute, I did see batteries in there. There were 2 batteries, which I assume are backup batteries in there, which I measured. They both showed close to 3 volts. And since usually static RAM, which is used in battery back mode to save the state of the instrument, needs approximately, will work at down to a minimum of 2 volts, even taking blocking diode drops into account, 3 volts is more than plenty to keep it going, and that's what happened. It saved the state of the scope and brought it right back when I turned it back on. So bonus, the backup works in it. Anyway, I hooked it up to a function generator that is currently displaying a 50 kilohertz sine wave. So let's turn it on, and we can see it displaying a very nice looking sine wave. I need to add that one of the things I noticed was that the screen was a little bit weak. It is currently cranked up to almost maximum, both the background and text as well as the signal itself. But that's what you get from a used scope that probably saw heavy use and was running 24/7 for very long periods of time. Could be a function, could be a bunch of items that cause this. The high voltage may have dropped a little in this. The tube may need a rejuvenation. I don't know, and it really doesn't matter to me right now because it is bright enough. It's actually showing up a little bit brighter in the video than it is in real life, but it's a nice green on black display, and that is very easy to read right now, so I'm not going to deal with any tube issues right now, with any CRT issues right now, unless it becomes necessary in the future. Now we can also look at the acquire menu here, which lets you specify how to show the waveform. Now the reason for that is remember, this is a digital scope, and unlike an analog scope which uses an XY display, this uses an actual a raster display, just like your television or your computer monitor. A raster display has a finite resolution, in that rather than an analog display where you can draw a line segment from anywhere to anywhere with near infinite resolution, your resolution is basically limited by what the screen allows, and it's creating, just like a video game, it's creating a screen map of pixels that is updated at, I would assume it's, the screen is probably updated around 60 Hertz or 120 Hertz, but it will make you see a lot of things that an analog scope will automatically smooth out, but a digital scope will not. Now in a digital scope that is a desirable property, because when you are capturing a single frame of a waveform or a glitch or a digital transition or something like that, you want to see exactly what's happening in there. And in a case like that, you would use the sample mode. And the sample mode, can't really see it in the video probably, but it gets a little bit more jittery because it's actually showing you a one-to-one display of what it is sampling, of how it is sampling the signal. Now you can go and average it, and you can change the number of averages. It's set to 16, and it's a pretty clean display. I don't see a whole lot of jitter or noise on it, but when watching, just watching waveforms rather than single things happening, such as I said, such as you're looking at a glitch or anything like that, the best thing to use on this is to go into the high-res mode. And in the high-res mode you get a very clean display. It does internal noise filtering on it and all of that, and again, looking at a recurring waveform, it looks as nice as an analog scope, I would say. So we can get rid of that. We can still scale the waveform. Now in this case I'm beginning to see noise riding on top of the wave. Not bad, but it is there. And for completeness, we'll put up a square wave. Looks like we need a little bit of probe compensation here. The trigger point marker can actually be very useful. In this case, you know, it's jumping around, but that's because we have such a fast rise time on the square wave that it is triggering at this instant in time, but this instant in time is taken up by the rise time of the waveform, and so it's jumping around. But if we move on to a triangle wave, we can see that the trigger point is very steady, and as we change the trigger level, we will see it wandering up and wandering down the wave. I usually leave it in the middle because that gives you the best chances of getting a trace on the screen when nothing is showing up. Well, all of that said, looks like this guy came out pretty nicely, and has also earned a place on or around my test bench. And these, again, as I said at the introduction, these scopes, the TDS series of scopes, they are available on eBay, but you should be aware that if a lot of sellers will show the startup screen and tell you, hey, it's powering up but not working correctly. And if you see any complaints about the acquisition board, it will most likely be that the caps have started to leak electrolyte, and that electrolyte has maybe disconnected well, damage at least some of the traces, and that finding that problem can be hit or miss. I must say I was lucky that when I measured and traced the voltage regulators, that was the actual problem, which was fixed pretty easily and seemed to have been the problem. The problem that persists is, even though I cleaned up the board a lot, I cleaned it with vinegar, then gave it a bath with 99.9% isopropyl alcohol to get rid of the vinegar and hopefully neutralize everything, but there are still traces of the leaked electrolyte in there, and that might turn around and come back to haunt me in a while. But the instrument was cheap, it looks very nice right now, and we'll just hope that I get years of service out of this. Well, if you like what you saw, and or you learned something and want to see more, go ahead and subscribe, because that's basically what I need to encourage. I need that sort of encouragement to make more videos. You could also click on the like button. That's also a good thing. And we will see you at the next video. I don't know what it's going to be yet, but if you subscribe, you'll be the first to find out. See you later.